Let's go over 8 examples where we have to use the ratio test or maybe the root test to help us to see if a series converges or not. Here's the first one. The series as n goes from 1 to infinity of n over 3 to the n. It does look like a geometry series, right? And you can really say this right here is greater than or equal to the series as n goes from 1 to infinity of 1 over 3 to the n. But the problem with this is that this right here actually converges because the common ratio is 1 over 3. And this is greater than because n is greater than or equal to 1. Yeah? But the thing is, it does not help us to draw any conclusion. When you say this right here is greater than a convergent series, you are saying this is greater than a finite number. Well, it can be just a bigger finite number or it can be infinity. We cannot draw any conclusion. So in this case, we can actually try the ratio test. Why the ratio test though? Here's the key. When you have n in the exponent, maybe you want to give it a try. Or maybe the root test. But the root test, you will have to take the nth root of n, not the prettiest, so ratio test might be better. When you have n in the exponent or factorial, try the ratio test. So by ratio test, we are just going to do the following. This right here is our an. So we are going to check the limit as n goes to infinity. And remember the ratio test is that it's the absolute value of an plus 1 over an. We can write it as an plus 1 times 1 over an. So the n plus 1 term, plugging, and then times the reciprocal of the original. So this right here will give us the limit as n goes to infinity. The absolute value doesn't matter because here everything's positive. Yeah, n is 3 to the n is positive. An plus 1, you just put n plus 1 into here and here. So n plus 1 over 3 to the n plus 1 times the reciprocal of the original. So just do that. 3 to the n over n. Now check this out. 3 to the n plus 1, we can break it apart as 3 to the n times 3 to the first. Moreover, 3 to the n cancel. So we are looking at the limit as n goes to infinity. On the top is just n plus 1. On the bottom, we have 3 times n. Now, as n goes to infinity for this kind of limit, just compare this and that, which is going to tell us the limit is 1/3. And when we get the limit of this being equal to less than 1, not equal to. If it's equal to 1, the ratio test cannot help us draw any conclusion. This right here is less than 1, therefore we can say this right here converges. And we know this limit cannot be negative because we apply the absolute value already. So right here we can come here and say this series converges by ratio test, but do not abbreviate ratio test because root test is also RT, so just spell it out. By ratio test. Now for the second one, we see the factorial and we see n in the exponent, so definitely try the ratio test. So here is our an. Here I will just say we are going to check. And let me write down what we are going to check again for you guys. The limit as n goes to infinity of the absolute value of an plus 1 times 1 over an. So we see that this is the limit as n goes to infinity. The absolute value doesn't matter because again, everything is positive. An plus 1, just put n plus 1 here and n plus 1 here. So we get 2 to the n plus 1 over here. This is n plus 1 that we're entering, yeah? We also have to enter the n plus 1 here. But it's another plus 1. And then after that, we do the factorial. And then the reciprocal of that, which we have n plus 1 factorial over 2 to the n. So this right here is really just n plus 2 factorial. And now how do we break this apart? Well, we can write this down as n plus 2, and then times the next term, which is n plus 1, and then times the next term, which is n, and so on, so on, so on, which we can say is n plus 1 factorial. Always try to break down the bigger factorial and also the bigger exponent. Likewise here, this is 2 to the n plus 1, which is 2 to the n times 2 to the first. Now, happy canceling. 2 to the n cancel, and then n plus 1 factorial cancel. Have a look. Here is the limit as n goes to infinity. On the top, we have this 2 to the first power, so it's just 2. No more, and on the bottom is n plus 2. As n goes to infinity, we have 2 over infinity. So in this case, the limit is equal to 0. And now you have to remember, we are doing the ratio test. If the limit that we get is less than 1, this is all we need to say, and that tells us it converges. So come back here and we'll say this right here. Converges by the ratio test. It's the limit comparison test that we cannot say anything if the limit is equal to 0. But for the ratio test, if the limit is equal to 0, we can still draw a conclusion. As long as the limit is less than 1, that series converges. Now for number 3, series as n goes from 1 to infinity of 2n plus 1 raised to the nth power over n raised to the 3n power. This time, we have both n in the power here and here. So it would be a better idea to use the root test, because when we take the nth root, they pretty much get cancelled. Yeah? You can still try the ratio test too, but I will leave that to you guys. So here we go. We are going to use the root test. So what we are going to check is the limit as n goes to infinity, and we take the nth root, and then here, just in case sometimes we have negative stuff, but don't worry, we will take the absolute value. Take the absolute value, and again, this right here is our an, and we're just going to put the an in here. So here we go. We will do the limit as n goes to infinity, and then we take the nth root. The nth root, which is the same as the 1 over nth power. Very nice. The absolute value doesn't matter in this case because everything is positive, so we can just write this down, which is 2n plus 1 raised to the nth power over n to the 3n power. Now, because we have this over that, so when we do this power to that power, n and 1 over cancel. Likewise, when we do this to that power, n and 1 over cancel. So we are looking at the limit, n goes to infinity. Here is just 2n plus 1 on the top. On the bottom, it's just n to the third power on the bottom. Now, as n goes to infinity, you care about this, you care about that. It reduces to 2 over n squared, and as n goes to infinity, we get 0. And for the root test, as long as the limit is less than 1, we get to draw a conclusion that this right here converges by the root test. Now for number 4, the series as n goes from 1 to infinity of negative 4 raised to the nth power, and then here we have 3n squared. Firstly, you can rewrite this as the series as n goes from 1 to infinity of negative 1 to the n, yeah, because this is like negative 1 times 4. And then here we have 4 to the nth power over 3 to the n squared power. You can do that. And you can try to do this with the alternating series test, but well, in this video, we are talking about either the ratio or the root. Here, we have n in the power, so a better way is the root test. Here we go, we are going to check the limit as n goes to infinity, the nth root along with the absolute value, and then we put the an inside. I'm just going to write this down for an. So this is the limit as n goes to infinity. The nth root is the same as the 1 over n power on the outside here. And then the top here is negative 1 to the n, and then 4 to the n over 3 to the n squared. Here, I'm still going to keep the absolute value because I'm actually going to use the absolute value to get rid of this term. Negative 1 to the nth power is negative 1 plus 1, negative 1 plus 1, right? So when you have the absolute value for that, this is just going to be always 1. So we are just going to get, let me just write down one more line to make it super clear. So focus on this to the 1 over n's power, and then 4 to the n over 3n squared. Alright, now 4 to the n raised to the 1 over n and n cancel. Yeah, so this is going to be, I'll write this down here. Just 4 on the top, and on the bottom, this right here is 3 to the n, because you can just divide this by n, so n squared over n. That's how we get the n right here. Okay, and then as n goes to infinity, the bottom here is 3 to the infinity, which is infinity. On the top is just 4. So this right here gives us 0. Therefore, we know it's less than 1. Therefore, this right here converges by the root test. Now for number 5, we have the series as n goes from 1 to infinity of 1 over square root of n factorial. So this right here is not p-series. Do not say this is n to the 1/2 power because we have the factorial inside. And because we have the factorial, try the ratio test. So here we go. We check the limit as n goes to infinity, and then what we do is the absolute value of an plus 1 times 1 over an. So this right here is our an. So now this right here is the limit as n goes to infinity. Absolute value doesn't matter because this is always positive. An plus 1 put in here, so we have 1 over square root n plus 1, and then we do the factorial times the reciprocal of the original. So we get just square root of n factorial over 1, like that. And let's put on over 1, why not? Now break down the bigger factorial. But this time though, they are still inside of the square root. So we are looking at square root. This is n plus 1 times the next term, which is n, times the next term, which is n minus 1, and so on, which is just n factorial. N plus 1 factorial equals n plus 1 times n factorial. And this right here is just the same as square root of n plus 1 times square root of n factorial. And you know, this and that can cancel. So we get the limit as n goes to infinity, 1 over square root of n plus 1. As n goes to infinity, this limit gives us 0. We have less than 1. Therefore, this right here converges by the ratio test. Now for number 6, the series as n goes from 1 to infinity of 3 to the n over n times 2 to the n. Again, this is not a geometric series because we have this extra n multiplying 2 to the n. And you might try to do some comparison tests, but I will leave that to you. Here, let's try to use the ratio test because I really don't want to deal with the nth root of n, right, as n goes to infinity. So ratio test will be the way to go. We check the limit as n goes to infinity, absolute value of an plus 1 times 1 over an. Alright, so I'm going to just put n plus 1 into all the n's. So this is the limit as n goes to infinity. We have 3 to the n plus 1 over n plus 1 times 2 to the n plus 1. and then the reciprocal of that, which is n times 2 to the n over 3 to the n. Now break things apart. This right here is 3 to the n times 3 to the first. This right here is the same as 2 to the n times 2 to the first. 3 to the n cancel, and 2 to the n cancel. Alright, this is the limit as n goes to infinity. On the top, we have 3n. On the bottom, we have 2 times that, so it's 2 times n plus 1. So in this case, we are actually looking at the limit as n goes to infinity. Let me just multiply this in to make it super clear. This time, as n goes to infinity, as we can see, the limit is 3 over 2, and that is greater than 1. Therefore, this series diverges. By the way, this is a, and I should have circled that to keep my video consistent. Anyway though, this right here diverges. Like the first one in this video, right? Diverges by ratio test. Now number 7, the series as n goes from 1 to infinity of n factorial over n to the nth power. Because of the factorial, it's a great idea to use the ratio test. So this is our an, right? Let me circle that, and then we check the limit as n goes to infinity of the absolute value an plus 1 times 1 over an. So we get the limit n goes to infinity. Absolute value, again, doesn't matter, and we will just have an plus 1, so n plus 1 here, and then we factorial that over n plus 1 raised to the n plus 1, and then times the reciprocal of that, which is n to the n over n factorial. Now for the top, it's just n plus 1 times n factorial, so you know this and that can cancel. But for this one, it's a little bit stranger, right? I can break this apart as n plus 1 to the n times n plus 1 to the first. And then in this case, we can happen to cancel n plus 1 here. But we cannot cancel this and that. So be careful with this. But now we are looking at the limit as n goes to infinity. Notice how they both have the n in the exponent. So we can write it down as n over n plus 1 and then raised to the nth power. Again, because of this n and that n. How can we deal with this though? If n goes to infinity, the inside you get 1, but n goes to infinity. In fact, this is a 1 to the infinity indeterminate form. We cannot draw any conclusion right now. And the idea is that we can actually use one of the secret weapons that can help us out. And let me write that down right here for you guys. I call that the fact. It's a very useful limit fact. It's a limit as n goes to infinity of 1 plus a over n raised to the bn's power. Here you get 3 letters, e to the a b's power. So I'm going to show you how to put this into this form. First though, we are going to flip the fraction inside, so we get the limit as n goes to infinity, and I really want to have n plus 1 over n like this. So I can split the fraction. Well, all we have to do is just negate the exponent. The negative exponent allows us to flip the fraction. Now we can split the fraction. This is the limit as n goes to infinity of n over n is 1 plus 1 over n, and then raised to the negative nth power. Now this is in this form, and we can say that a is just equal to 1 and b is negative 1. Therefore, the limit for this is e to the 1 times negative 1, which is negative 1. And for this one, you have to be careful. e to the negative 1 is 1 over e. And because we're doing the ratio test, you mention this right here is less than 1, and you come here and draw the conclusion that this series converges by the ratio test. And then we are done. Now for the last one, we have this. Now for the last one, the series as n goes from 1 to infinity of 1 plus 2n over 3 plus 4n, and then raised to the nth power. Don't you just really want to get rid of the nth power? I would totally do so too. And to do so, we use the root test. So here, we are going to check the limit as n goes to infinity, and then we take the nth root, and then here we have to put the absolute value, and then the an. This is the an, and then just do it. Here is the limit as n goes to infinity. The nth root is the 1 over nth power, and the absolute value doesn't matter because everything is positive. And I will just put down 1 plus 2n over 3 plus 4n, and then raised to the nth power. The beauty for this is this and that cancel right away. So we are going to get the limit as n goes to infinity, and then we have 1 plus 2n over 3 plus 4n. Then for this limit, we just need to worry about 2n and 4n. Reduce, you get 1/2, which is less than 1. And we can come here and say this right here converges by the root test. So that's it. Hopefully this video is helpful. If you have any questions, feel free to leave a comment down below and let me know.